Alright guys, here we go with 2.8 video, proportions and similar figures. After this lesson I need to be able to find the missing links in similar figures, use similar figures when measuring indirectly. Alright, here we go. Sailboat and an accurate model of the boat are shown. What is the length of the model sailboat? Explain your reasoning. Okay, so here's what I have as an actual sailboat here, and then I have a smaller version of the model of the sailboat. So here we go. Well, the height of the model sail is 4 feet. So this is the model. The height of his sail is 4 feet. The height of the actual sail is 12 feet. Okay, so the actual dimensions are 3 times the model dimension. 3 times 4 gives me 12. So the actual thing is 3 times as big as the model. All right, so the question then becomes, is the model boat length times 3 has to equal the actual boat length. So this number, whatever it is, times 3 has to get me this number. Well, that's pretty easy. The model boat length times 3 has to be 9. So that means that the model boat length would have to be 3. Okay, that's pretty easy. That is using a similar figure. So you can use proportions to find missing side lengths in similar figures. Such figures can help you measure real-world distances indirectly. So here we go. In the Solve It, the sailboat and its model have the same shape, but they are different sizes. So basically, the real sailboat was shrunk down to create this one right here. Okay? Similar figures have the same shape, but not necessarily the same size. So when we talk about similar, that's what that means. That means they have the same shape, but not necessarily the same size. All right, and then this symbol, this is called a tilde. That symbol means similar to. All right, so let's look at the picture here. Triangle ABC is similar to triangle FGH. So same shape, but not the same size, okay? So anytime we have similar figures, 2 things are true. 1, the corresponding angles are congruent. So whichever angles match up, those are the same size. And the corresponding sides are proportional. So I can multiply the same number to get from one picture to the next. All right. The order of the letters is important because it tells you which parts are corresponding or which parts match up. So if you were to look at ABC is similar to FGH, well, that means that angle A, the first letter here, matches the first letter here. So angle A is the same exact size. That's congruent. That symbol right there is called congruent. Means the same size as angle F. Angle B, second position, is congruent to the second position here, B and G. And then C is congruent to H. C congruent to H. Third position here, third position here. So the angles are congruent. The sides are proportional. So in this picture, AB, the ratio of A over B, is this, and FG, so this ratio between here and here, is the same as any other set of corresponding sides. So 10 to 15. All right, again, if you look at the letters, first 2 letters here match with the first 2 letters here. First and third match with first and third here, FH. Second and third match with second and third here. Okay, so the order of the letters is definitely important. It's easy to see when they have the 2 pictures, turned the same way. But if they were to flip this around, it might be harder to see. So you need to see those letters. They'll help you see which things match up. In the diagram, triangle ABC is similar to DEF. And they're asking me, what is length DE? So I have to find this side. Well, I know I can set up a proportion because the corresponding sides are proportional. So BC, this side, compared to EF, 16 over 12, is in the same ratio as 10 is to the side that we're missing. Okay, so I can set up a nice little proportion. This 18 I don't need right now. He doesn't really help me. AB matches up with this side, DE, right there. So here's what we have. We have a 16 for the BC. We have a 12 for the EF. We have a 10 for the AB, and we're looking for this. So I would just make that a letter, like a variable, X. Now I have a proportion. So hopefully we're getting pretty good at solving proportions. Cross multiply. Okay, so I got 16 times x is 16x, 10 times 12 is 120. Solve it, divide both sides by 16, and x is 7.5. I knew that this had to be smaller than 10 because 16 and 12, well, this triangle has sizes that are smaller than this triangle. So this definitely had to be smaller than 10. So 7.5. Okay, in the next example, it says, what is AC? So AC is this bottom length here. So he matches up with this bottom length here, which is DF. Okay? If you look at the letters, AC, first letter, third letter, he matches up with first letter, third letter there. So AC matches with DF. Okay? I still need another set of numbers because I can only have one missing part to my proportion. So I'm still going to use the 16 and the 12. All right, you could have used the 10 and the 7.5 that you just figured out, but I usually always try to use the numbers that they give me. So BC, this compared to this, is in the same ratio as bottom here compares to bottom here. So filling in what we know, 16 over 12 is the same as this over 18. Well, I'm just going to make that a letter. So instead of having AC there, I'll just make it a variable x. So now I have a proportion. Cross multiply that bad boy. All right, make your equation. 12x equals 288. Divide both sides by 12, and you got x to be 24. Okay, now notice in this picture, the 18 is more than 12. Right, so the bottom is bigger than the side. So here, the bottom has to be bigger than the side. Okay, and we knew this triangle had bigger numbers than this triangle. So I knew my answer for AC would have to be bigger than 18. Okay? So it really just comes back to making a proportion and then solving a proportion. We can also use proportions to solve indirect measurement problems like finding a distance using a map. We can use similar figures and proportions to find lengths we cannot measure directly. So for example, a sun's rays strike the building and the girl at the same angle, forming two similar triangles shown. How tall is the building? So I can't really measure this building without going onto the roof. Okay? But I can use this idea that this triangle is similar to this triangle. So the sides are proportional to find this missing length of the triangle. Well, if we look at the girl, the height of the girl and her shadow are in the same ratio as the height of the building and the shadow of the building. All right? So if we look, I got 5 for the height of the girl, 3 for the shadow of the girl. So 5 over 3, same ratio as height of the building over shadow of the building. So as long as you're comparing the same things on the tops and on the bottoms, it's easy to make your proportion. You could definitely put shadow of girl on top and height of girl on the bottom, as long as you do shadow of building on the top and height of building on the bottom of this one. Okay? Now it's just a proportion. Cross multiply that bad boy. Solve that up. 3x has to equal 75. Divide by 3, and x is 25. I knew that the building would be more than 15 because the girl's height is more than her shadow. The shadow of the building is 15, so the height had to be more than 15. That makes me feel good about my 25. Okay? All right. A man who's 6 feet tall is standing next to a flagpole. The shadow of the man is 3.5 feet. The shadow of the flagpole is 17.5 feet. What is the height of the flagpole? All right, let's break that down. There's a lot of stuff in there. So the man is 6 feet tall. There he is. Hey, dude. He's 6 feet tall. He's standing next to a flagpole. Oh, there he is. There's the flagpole. All right. The shadow of the man is 3.5 feet. The shadow of the flagpole is 17.5 feet. Okay? What is the height of the flagpole? So I'm looking for this height right here. Okay? To me, it's probably easiest if we break that apart into those two triangles. So that's kind of confusing maybe. I'm just going to break it apart so that they're two separate triangles. Notice I'm looking for height of the flagpole right here. So the man, his shadow, the height of the flagpole, its shadow. So I know the man is 6, his shadow is only 3.5. So the flagpole is going to be taller than 17.5. I know in this picture it doesn't look like that, but look at it. The man is 6, and his shadow is only 3.5. The flagpole has to be taller than its shadow. All right, set up your proportion. Height of the flagpole over the shadow of the flagpole equals the height of the man over the shadow of the man. Again, you could put shadow of the flagpole on the top and the height of the flagpole on the bottom, as long as you do shadow of the man on the top and height of the man on the bottom. Okay, so it doesn't matter how you set up your proportion as long as you're comparing like things, corresponding parts really is what they would say. So here we go with some numbers. X over 17.5. Height of the flagpole is what I'm looking for, over its shadow, equals height of the man over his shadow. 6 over 3.5. It's a proportion. Cross multiply that bad boy up. I got an equation. 3.5x equals 105. Divide both sides by 3.5, and x is 30. Again, we knew the flagpole had to be taller than the shadow because the man is taller than his shadow. So the flagpole is 30 feet. Okay? A scale drawing is a drawing that is similar to an actual object or place. Floor plans, blueprints, maps, those are all scale drawings. In a scale drawing, the ratio of any length in the drawing to the actual length is always the same, and a ratio is called the scale of the drawing. So again, we're just going to basically create some more proportions. So here's where you see a lot of that with a map. So what is the actual distance from Jacksonville to Orlando? Use the ruler to measure the distance from Jacksonville to Orlando on the map below. And then notice there's a scale right here. 1 inch is equal to 110 miles. Okay, so from Jacksonville to Orlando is 1¼ inches. All right, according to my ruler. So the map scale, 1 inch is to 110 miles, equals the map distance over the actual distance. So this map scale is going to be a ratio, 1 inch over 110 miles. This distance here was given to me in inches. That's the map distance, and I'm trying to find the actual distance. So it looks something like that. 1 inch over 110 miles, that comes right from the scale, equals 1.25 or 1¼ inches over how much? So this is actual distance on the bottom. Actual distance, 110 miles. Scale, map distance, 1 inch. Map distance, 1.25. I'm looking for the actual distance. It's a proportion. Cross multiply, bad boy. So 1x equals 137.5. This is a nice problem because you don't have to worry about dividing because you only have 1x here. All right, so 137.5 miles. Okay, here's another one. Distance from Jacksonville to Gainesville on the map is about 0.6 inches. What is the actual distance from Jacksonville to Gainesville? Well, same idea. You have a scale from the map. 1 over 110. So 1 inch over 110 miles. So map over actual equals map over actual. All right, it's 0.6 on the map. That's why it's on the top. Cross multiply that bad boy. 1x equals 66, so it's 66 miles. There it is. The actual distance from Jacksonville to Gainesville is 66 miles. By the way, in Gainesville, you would find Gator Country, home of Tim Tebow, the man. Gainesville, Florida, home of the University of Florida. A scale model is a three-dimensional model that is similar to a three-dimensional object. The ratio of the linear measurement of the model to the corresponding linear measurement of the actual object is always the same. This ratio is called the scale of the model. So instead of a scale drawing, now you have a scale model. It's an actual three-dimensional thing. All right. The Please Touch Museum in Philadelphia. There's a giant model heart. The heart is the ideal size for a person who is 170 feet tall. About what size would you expect the heart of a man who is 6 feet tall to be? So if you look here in the picture, this is the model. It's 14 feet tall, the model. It fits a guy who's 170 feet tall. The question is, how big is a 6 foot tall man's heart? All right? So you have a proportion. Size of the model heart over the size of the model man equals the size of the actual heart over the size of the actual man. And so this is the scale that's going on here. So I have the size of the model heart was 14 feet. That fits a guy who's 170 feet. The size of the actual heart is the question. About what size would you expect the heart? That's what I'm looking for. The size of the actual man is 6 feet. Again, it's just a proportion. Solve that proportion. Cross multiply that bad boy. Bang, bang. 170x equals 84. You see there's so many proportions. It's all about cross multiplying. Divide by 170. X is about 0.494. Alright? So if the guy 0.494, about 0.494 feet is about 6 inches. Right? It's almost half a foot. Half a foot's about 6 inches. Okay? The scale model of a building is 6 inches tall. The scale model is 1 inch is to 50 feet. How tall is the actual building? So the size of the model building over the size of the actual building equals the scale factor of the model over the scale factor of the actual. So I'm going to use this idea. All right, there's my scale. The size of the actual building, of the scale model, is 6 inches tall. 6 over the actual building. I made it a B, so I reminded myself that's the building, not the model. The actual building equals 1 inch over 50 feet. Notice the 6 inches is on the top. The 1 inch is on the top. They have to be together. All right, you could do the 6 inches on the bottom, but then you need the 1 inch on the bottom. You know, the 50 up top and the B up top. It's a proportion. Cross multiply. We spend so much time cross multiplying. You solve so many problems that way. This is an easy one. 1 times B is B. 6 times 50 is 300. The building is 300 feet tall. Alright, dudes and dudettes, that's it for section 2.8. I'll see you next time. Peace.